Welcome to this session on what we are calling as embedded C. The reason we are calling as embedded C is because we're going to focus more on the parts of C which are quite often used in programming embedded systems. So there are a few parts of C which are quite heavily used. So we'll probably spend a lot more time on that and show you how to use those features really to program embedded systems. That's why we are titling it as that. The language itself, the syntax is pretty much standard C only. But the reason we call embedded is the focus on those concepts which are really important to understand thoroughly and how to use that effectively. Maybe if you're doing a general purpose programming, you may not probably do too many of those things in the regular course, but here it becomes important. So that's the whole reason we're titling it as embedded C. And we're going to go through the entire language, but we'll probably spend more time on those areas which are more important for the embedded programmer. Okay, so we'll just start with basics. First session is to understand what do you mean by data type in C. I'll first explain what is a data type and in C what are available. Then basic operators, what operators are available, and then simple how to read and write maybe from a general console type of a thing. And we'll also spend a little bit of time about type conversions because that's something important to understand, especially when in the embedded side. You need to really understand what goes on when you say type conversion. Okay, so that's going to be the agenda for the first module. Let's start first by looking at what is the basic structure of a C program, right? In any programming language, it's good to really understand. If I open a file, somebody tells me there's a C program, I open the file. It's good to understand what are all the different things that you can expect. Assume it's a very simple program, it's in one single file. Complex, bigger projects will have multiple files, we'll worry about that later. But to start with, if I open a C file, what are the things that I will typically see in a C file, right? Okay. So the first thing to remember is on the top of the C file, you will have a lot of statements called hash include. Typically, this left arrow and right arrow, within that some name of a file. Okay. So these are all called header files. Okay. So we'll quickly cover what it contains, but first let us understand what it is called. It's called header files. And in almost every C program, you will see this stdio.h. Actually, that stands for standard io.h. If you want to use functions like printf, scanf, you need to include that. Okay. Now, header files actually generally don't contain functions or code. They contain definitions and declarations so that when the compiler runs, for example, when the compiler is running and it is seeing this word called printf, right? There is information about what is printf in this file in stdio.h. So there is a line, we call it a declaration. That line will tell that printf is a function. It takes these many type of arguments. So the compiler has already seen it. Compiler, when it compiles a program, it will start from the first line and it will go through. And this include, what it really does is, instead of this line here, the entire contents of the file will come in that place. Okay. So that is why it is called hash include. Include means instead of that line, say assume stdio.h has 100 lines, for example, right? There is a way to look at the output of the first, this is called the first stage of a compilation. It's called the pre-processing stage. So there what happens is, instead of that one line, that entire 100 lines in that file will come there. So after the pre-processing output, you might have written a 10-line C program. If you see the output after the pre-processing stage, it will probably be 1,000 lines because if you have included some 5-6 different header files, all that code will come. And that is what goes to the next stage of the compiler. And the compiler would have gone through that stdio.h comes at the very beginning, right? So there's already one line there which tells what is printf. So that line will typically say, okay, printf is a function. It takes these many parameters and it either returns this kind of what is the return type and so on. So compiler knows what is printf. So when it comes here, when printf is being used in your code, it knows how to check whether the parameters are all these are all called function parameters. We'll see more in detail, but for now understand, include means the contents of the file come into that place. Okay, so that is why it's called hash include. Typically, what are called declarations, global definitions, they're all available in those files. And stdio.h is something which you will see in almost every file. You will see some more something called stdlib.h, which has some standard library. This is also quite common. So you will see a set of hash includes at the very beginning of the file. Okay, hash includes should always come there because that code has to be there for the compiler's subsequent phases before you use any of those things. Is that clear? So hash include, these are called header file definitions. They are always at the top of every file that you have in C. Okay. The next step after all the hash includes, we have the global variable declarations. Okay. So a declaration is a place where you tell what is the name of a variable, what type it is, and so on. So we call it global variables because if you see, this is not inside any function. This program has got, say, a main function, function 1, function 2, but the global variables are all outside any code of a function. Okay. The reason we keep it that way is we want that to be visible for all the functions. So global variables are variables which can be accessed from any function in your code. Function is nothing but a small piece of code which does a particular type of activity. So global variables are those which are available for all the functions in your C program. Okay, so that comes. Then after the global variables, you typically will have a set of functions. Each function, the code will start with this curly braces, left curly brace, and will end with this curly brace. Okay, so this here you will have the function name, and you'll have a start curly brace and end curly brace, and the code will come here. And in each, for example, if you see function 1 here, right? Function 1, we have defined the name function 1, and there is a curly brace, there is a closing curly brace, and then you have all the local variable declaration. So you can have variables within the function. What are local variables? Those are variables which are only accessible by the code within the function. Okay. So those are called local variables. Don't worry too much, we'll go into details again. But right now, just understand a C program is nothing but set of header files, global variables, and set of functions. And one function is special in C. What is that function? A function called main. Every C program should have one function called main, which is where the code starts running. Even when you run any platform that you run, typically by convention, main is the place the code should start running, at least on a standard platforms like Linux or whatever. That is where the user's code starts running. Okay, there may be something else which is running before control comes to main, but from a user perspective, for us, code execution will start at the main function. Okay, main function takes some arguments which are called argc and argv. These are typically used for things like command line. Like if you have a Linux console, you can type your program and give some arguments on the command line, right? So those command line arguments are processed using these variables. Don't worry about those things too much now. But for now, if you have to understand a C program, any C file that you open, .c file, so you open a file called x.c, you will typically see these things. You should see a set of header mostly. I mean, if the code doesn't need it, may not be there, but you will typically see them. Then you will see a set of functions. If this is your only program, for example, you are having only one program, one file, that's our entire program, you should definitely see one main function in that program. Is that clear? So any C program in the world, you can break it down into these parts: global variables, header files, set of functions, which all cooperate to achieve the given functionality. Okay, is that much clear? So that's what is there in a C program. See a simple code snippet. Okay, so assume this is the body of your main function here. Okay, so I'm not showing the main name here. Assume this is your main function. The code starts with this opening curly brace, ends with this curly brace. This total thing is, say, assume one function, right? This whole thing is like one function's code is there here. Okay, now you can see this is called a variable declaration, which is within the function. So this is a local variable declaration. We'll see a little bit more about declaration shortly. And then these are called assignment statements. I'm assigning a value to a variable. I'm doing some operations here. Here you can say this is called as a decision statement because I'm checking some condition and then taking some action. Just a typical example. Don't worry too much about it. Just to show you how typical C code looks like, right? Okay. So any function, you will have probably local variables and then some sequence of statements which are there. And one thing to remember is in C, this is a C statement, and every C statement, one thing to remember is it ends with a semicolon. Is that clear? Any C statement will end with a semicolon. Something which is starting with a curly brace and ending with a curly brace, a block of code here, we call it as a compound statement. Okay. So for example, if this if and there is a curly brace and a closing curly brace, I can have some 10 statements here. In this case, there is only one, but those 10 statements together is generally called as a compound statement. A statement in C can be either a simple statement or a compound statement. A simple statement is one line of code which ends with a semicolon. A set of lines enclosed in a curly brace path is called as a compound statement. Is that clear? So these are terms which are good to remember because it will be useful later. Statement, then simple statement, and compound statement. Because once you understand this, a lot of the syntax becomes easier to understand. So this here, for example, you can say is a compound statement which has only one single statement. But I could have had one more printf here also, something. So this becomes a compound statement with two simple statements. Okay. So is this clear? How a typical C code snippet looks like? Now we'll move on to data types, right? Okay. So we already saw when we looked at the basic of computing and all that, right? We want to deal with numbers, text. Those are all the things you want to process. That's why computers were invented, right? You wanted to process maybe numbers, do some calculations, or process some text, write an editor, print something. So those are all the things. The sharing is working, right? Okay. So those are all the things that you want to start processing, right? Now to process information, it needs to be stored in a particular place. And so you need to use it, use the appropriate amount of space for storing things, right? So for example, we saw the other day, like a character, like we talked about ASCII characters, right? We talked about ASCII characters, which are like, 1 byte, right? To store text in ASCII format, you need only 1 byte of storage, okay? So for example, if I want to deal with large numbers, okay, assume my machine is a 32-bit machine. So I want to deal with fairly large integer numbers. Then I probably want to use a data type where I can deal with 4 bytes at a time. Or say I am doing only computation with very, very small numbers. 16 bits is enough for me. So then there is a data type to deal with only 16-bit numbers. So basically the data types are things which essentially tell like what is the amount of storage and what is the type and processing that you can do with it. Okay. So there are languages where the type is automatically detected at runtime. Python, for example, there is no need for you to tell anything about a data type. So those are some model languages where the type is automatically determined at runtime. But C is a statically typed language. And statically typed means when you write the code, you tell what is going to be this data type. So the compiler is very clear, and it helps. Statically typed languages in some sense are good because you are very clear about what type you are doing. So the compiler can start checking things appropriately, that you're assigning the right things. If you're trying to assign a wrong value, it will tell you, this is probably not appropriate. So C is a statically typed language, and there are set of standard data types which are available. The reason we have data types is you can choose the right one for your operation. You don't have to waste memory. For example, I'm only going to do operations with small numbers which are not going to be more than say 255 positive number values. I can just use a data type which has just 1 byte because I know all my computation is going to fit within 1 byte, right? So suppose I want to operate on say floating point numbers, right? C supports floating point. There are data types to support and process floating point computation. Floating point is nothing but the decimal points, right? So if I want to do that, there's a data type for that. So that way, the data types tell the programmer what are the possibilities that are available in the language. So there's a set of standard data types defined in C. So as a programmer, we need to understand what those are. And it's good to also know what amount of memory they consume on that particular platform that you're working on. Especially in an embedded designer, you have to be aware of that because you don't want to waste memory, right? Suppose your embedded system is not going to deal with numbers more than 255. For example, you're reading a sensor and you know that value is going to be maximum 255 at any point of time. There's no need to store for a bigger data type for that, right? You can use a data type which is just allocates 1 byte of memory, right? So that is the reason for an embedded programmer, it is good to understand the data types, the amount of bytes each data type takes, and use the right one so that you don't waste memory, and you also know what exactly is happening, where it is getting stored, and so on. Okay, so that's the broad intro about data types. So as I said, data type specifies the type of data that is stored and the range of values. We'll see a chart which explains that. And in C, as I said, we have to specify. You can't declare a variable in C without telling its type, right? We will see how a variable is declared. You will see that soon, how a variable is declared. The first thing which will come in a variable declaration is the type. We'll first say the type, then the name of a variable, right? Okay, see, it is very important. And some examples like int means it's a integer variable, and the size of int depends on the platform. Most platforms in modern days it's 32 bits. Olden generation could have been smaller, but today mostly an int is 32 bits actually, which is 4 bytes. You have something called long, which is typically 64 bits on the modern laptops that we have. Float means it's a single precision floating point. Okay, there are standards how a floating point number can be represented. There's a standard called IEEE 754. So I think if you read the standard, you'll understand how it is stored. And there is something called double, which is double precision floating point. There are many more. We'll see that quickly. And thing to important, as I said, is to know that each data type has a fixed amount of memory and a representation format associated with it, right? Because int has a particular way of representation, floating point has a different point of representation. So you have to understand that each of the data types has a different representation. So a float variable, for example, occupies 4 bytes, double occupies 8 bytes, and so on. So important thing to summarize, the data type is nothing but which tells what type of data can be stored and the size that it occupies in the representation. And in C, any variable has to have a type. You cannot have an untyped variable in C. Okay. So we'll now see the list of things which are available here. Can you see this chart? So starting from here, the first one is called char. The second is called unsigned char. Okay, both occupies one. This is typical size in bytes. The example I have taken is a 64-bit machine. If you're an embedded platform which is 32-bit, some things can be different, but it's always good to understand. That's why you have to read the manual. The C compiler also will have options how to generate the code. Modern C compilers tell you what should be the space allocated for int, long. Sometimes it's configurable. There are options available. But this is a typical one. Char is generally always 1 byte. There's no confusion. The difference between char and unsigned char, can you see this? Char, when you declare a data type as char, it's treated as a signed quantity. Okay, when you do operations on that, when you do comparisons, it's treated as a signed number. It's important to understand this difference in C, because there could be cases where if you don't treat it as a signed quantity and do certain operations, it may not work as expected. If you want the variable to store only positive values, you can declare it as an unsigned char, and you can see the range that can be stored. If it is a signed value, you can store from -128 to 127, whereas unsigned char you can store from 0 to 255. And this we saw in the previous session, right? So how does this is 1 byte is what? 8 bits, right? So 255 is nothing but 2 power 8 minus 1, which is actually 255. Okay, that's how the size comes, because all 8 bits are available to store the magnitude. So this is a quantity that you can store. Moment you go to the signed representation we saw yesterday, 1 bit is taken away for the sign bit, right? The first MSB is taken away for sign. So we have only 7 bits. So generally, then the range reduces. So it's basically 2 power 7 minus 1 is the highest positive number. So which is like, 127 here. And on the negative side, you can go up to -128. Okay. So this is for char and unsigned char. Similarly, short is again integer data type, where it takes 2 bytes of storage. 2 bytes give you 16 bits. Okay. That's why you have this range. Unsigned is 2 power 16 minus 1. Whereas if it is signed, it's 2 power minus 2 power 15 to 2 power 15 minus 1. Okay. Then int is 4 bytes. So the numbers, as you can see, it's much bigger. Can you see the number? It's a much larger number because it's 2 power 31, or here it is 2 power 32, it's even bigger. Can you see? So it depends on the range of numbers that you want to operate. If you're going to, all your numbers are going to be within, say, 65, 535, you can just do the short data type and save memory because it only use 2 bytes. Similarly, long is 8 bytes. And you can see I have not written the number here, it will be much larger. So this is the range that it supports. Unsigned long is again 0 to 2 power 64 minus 1. Float is 4 bytes. And this is the numbers that you can store. It's minus 3.4 and to 3. This thing, and double is here actually. So basically, you can see the double can really store large numbers. There is a certain amount of precision. There's something called mantissa and exponent. So mantissa, there's a certain precision you can get. Exponents are bigger. So it again depends on what you want to do. So if your floating point computation is good enough, suppose the kind of work that you're doing is not too high precision, right? You can choose a float data type. Suppose you are going to work with some very, very high precision calculation. Say you are doing the rocket trajectory calculation, right? Where even a very, very small error can cause a huge deviation. Then you use a double precision. So it depends on the type of things that you want. Maybe simple calculations, float is okay. Very high precision things, you have to use double data type. Is this clear, this chart? So the reason we looked at yesterday those byte sequence and all that to understand it. For example, say int is 4 bytes. So if I declare a 4 byte variable, it will occupy 4 bytes in memory, right? But NDNS and all, if you store an int in memory, you should know how it is going to be stored. Depending on the NDNS of the processor, the sequence will vary. The lower LSB in low address or not depends on the NDNS. So is this data types clear? Any? Can we move on? Okay. So data types. This is the part of standard things which are supported in C. Next, we'll move on to, we have seen the data types. Why do we have data types? To store information, different types of values. How do you store information? See, in any program you want to manipulate data, right? So what are variables? Variables are nothing but, you can say, names for location where we are storing value, right? In a very simplest definition for a variable is nothing but a name given to a location where we are storing some value that we want to operate, okay? So there's nothing more complicated than that. So because you write a program to process some information, information means data, which is like, maybe 1 byte, 10 bytes, whatever, some amount of data that you want to process and get some results. So you have to store them somewhere before you can operate. So to store, you need some location, some addresses, and you give a name to that address location. That is what is called as a variable. Is that clear? So variable is nothing but a name given to a place where we are storing. And in C, you can imagine, C will directly map to, a variable will map to some address where the data is stored actually. Okay. So as an embedded programmer, it's important to understand, because later we'll see things like pointers. So it's always good to keep that in mind. When I'm storing something, it is always going into memory. Memory means each location memory has got an address. So suppose I'm storing, say, one byte, one character. I declared a character variable, right? It's just 1 byte. So somewhere in memory, the compiler and linker has given me 1 byte to store that variable. There is an address, but in a C program, I don't want to use the address directly. I generally want to use a name. So variable is nothing but a name that points to that address. That's all actually. So I just go by the name. I can operate actually. Okay. So let's look at, in C, we have to first declare the variable and specify the type before we start using them. Okay. So if you use some name without a declaration before, the compiler will give an error saying unknown, undefined name or something. It doesn't know what it is. Okay. So the way to use it is, first you have to do a declaration. And in general, variables are called identifiers. Identifiers in C are variable names are identifiers. Identifier, you can say a broad name, just means a name. Variable is a type of an identifier which calls a location. Then you have function names. Those are also identifiers. Okay, identifier just means it's a name for something. And there are rules to what type of, how an identifier can it start. There are some rules by how a name can be formed, right? It should not conflict with something else. We'll see that quickly. And these are, for example, examples of variable declarations. Okay, see what comes first. First the type comes, then you can have a series of names with comma. Okay, this is one type of things. Here you are declaring float type of variables f1, f2. So this tells x and y are variables where I can store a signed integer. You can, there is no need to write signed. You can write signed, no wrong. Even if you don't write signed, just say int, it means it's a signed quantity. Okay, signed is optional, nobody writes it generally. Float is always signed by default, so f1, f2. So this is character type. This is myBuf. This is something called as an array. We'll talk about it later. Array is nothing but a set of locations to store a similar data type. So this defines a array of characters by the name myBuf. Okay. So these are the important thing to remember is the type comes first, then a series of variables. We'll also see how they can be initialized and so on. Can you see that here? Another example, how you are declaring the variables and then you are using the variables. Is that clear? So int xy, we have declared two variables, and then I'm using the variable here. I'm actually trying to store a value 5 into x. This is called as an assignment statement. X equal to 5 means the value 5, which is like what is called as a constant, is stored in this variable called x. Basically, it's a location where 5 has been stored. And then what we are doing next, we are actually saying y equal to x. So y was other variable we declared here. When we say y equal to x, it's an assignment statement again. So what happens is whatever value was there in x, right, is now actually copied into y also. That value in x is assigned to the variable y also now. So basically after this, y and x will have the same one. So this is how you use variables. You first declare them, then we use them. So basically whenever you want to get the value of that, whatever value you're interested, you're stored in a variable. Instead of the value, you just give the name of the variable, right? So instead of x equal to 5, and we now just say y equal to x. I could have stored y equal to 5 also, but now I have stored this value in this variable. So that to get that value, I can just use the variable. So variable name is substituted by the value that is stored in the variable. Is that understood? Is that clear? Okay. And we can also initialize variables when we declare them. So this is an example of initializing at a declaration time itself, right? Here I am defining an unsigned int variable. There has to be a space between the unsigned key. These are all keywords. Unsigned is a keyword, int is a keyword. In general, these are reserved things for a language. So between unsigned and int, you have to have a space. Unsigned int. See the pattern here. We give the name, and we can immediately say equal to 2, and then comma y equal to 6. So instead of saying unsigned int x comma y and then later in the code initializing x equal to y equal to 6, you can directly do it in the same line. So this is a shortcut to initialize a variable at declaration time itself. Similarly here, float m equal to 3.14f. Okay, so what is this f? We'll see later when we look at constants. But these are examples of where we can assign the value wherever we are declaring them. So initialization at declaration time. This is the syntax. Is that clear? Syntax is nothing but grammar. I mean, every language will have a syntax. Syntax is nothing but the rules of the language, the grammatical rules of the language. So you can also see, important thing to remember is everywhere there's a semicolon. Semicolon is any statement in C is terminated by a semicolon. Is it clear? So we'll now go on to the next topic. We have seen how to use variables. And now let's see what's a constant. Okay. So we saw this example, right? We saw even in the previous slide, we saw an example of assigning something. We say int x equal to 213. It's a declaration. I'm also assigning. So this 213 is something called as an integer constant. Basically, constants are nothing but values that you use to assign to variables. And there are different types of constants. So if you just give a number, it's a decimal representation. So it is called as a decimal integer constant, to be technically correct. It's a decimal number 213 is getting assigned to the value x. Okay. So here we are declaring a variable long y equal to a slightly larger number we are assigning. Okay. Convention, if you have to be, this is not absolutely needed, but it's good to put L at the end so that you know it's a long constant, which means it's a big number. You can put a L as a long constant. And another thing to remember is if you write a number with a leading 0, right, then in C language, it means it's an octal number. We saw hexadecimal numbers yesterday. Octal is 3 bits together. In hexadecimal, you take 4 bits together. If you have a binary number, you take 4 bits together, group them, you get an hexadecimal pattern. Hexadecimal uses symbols from 0 to 9 and A to F. Octal uses only from 0 to 7. Okay. So in C, if you write any number with a leading 0, C thinks it's an octal number because the things here, it doesn't know. If you just write 37, it may mean it's a decimal number. So if you put a leading 0, it becomes an octal number. So octal 37 is actually decimal 31. You can convert and see. Octal numbers you convert using power of 8. So it's actually 7 into 8 power 0 plus 3 into 8 power 1. So 3 8s are 24 plus 7, 31. Okay. But this is one way to write it. If you put 0x, which means it's an hexadecimal constant. So basically, all these are, you can say the same value. In fact, 0x15 is what? 0x15 is again 16 plus 5 is, it's 21. But I'm just writing it in this way. Okay. So these are different ways to write a number. You can write it as a decimal number, octal number, hexadecimal number. And if it's a long number, you generally put an L to tell clearly that it is a long constant. Actually. Is that clear? So hexadecimal, as an embedded programmer, you will often use hexadecimal. So it's good to be comfortable with the hexadecimal notation, because it's very painful to take a binary number, convert it into decimal and write, right? When you look at an hexadecimal, you can quickly see the bit pattern almost visually. When I see 5, I can immediately imagine 0, 1, 0, 1. I know this is the pattern. When I see 1, I know 0, 0, 0, 1. So that 8-bit bit pattern is easy to quickly understand, right? So embedded programmers, if you're working in, when you say embedded C, these are all the important things, right? So 0x15, I can directly convert. 1, I write it as binary 0001, and 5 is nothing but 0101. So that's why hexadecimal is the most popularly used notation. So because you're dealing with bits, registers, and all that, right? So the moment you write it in hexadecimal, it's easy to understand and also write the code, develop the code. This much is clear. What are constant? I mean, numbers, that type of constant. The next type of constants are, floating point. We said C supports floating point data types like float and double. So a floating point constant will have this decimal point will always be there, right? That is what tells it's a floating point number. And typically for float, you will put this F here. In general, in C, if you write a decimal number, it is generally treated as a double constant, okay? Double precision constant. If you want single precision, you tell F here. That's the convention that the C compiler follows, okay? Same thing here. The data type comes first, then the name of the variable. Then you have what is called character constant. Character constants are nothing but where I want to store, so something in single quotes, right? If I write something like, say, single quote A, what really gets stored is the ASCII value of A. Okay, so if I want to easily store some characters and then process later, right? So I can use this notation, which is called the character constant representation, where I can take any of the symbols in the keyboard which are there and put in a single quote, and that becomes a character constant. But what really gets stored? The ASCII value of A gets stored, right? Because in memory, you can only store a bit pattern. So there's no way to store that A as it is, right? So what gets stored is really the ASCII value, ASCII code for A. That is what gets stored. Similarly, this is another way to store a octal number. If you put a \013, octal 13 is stored in C2. You can also, for characters, you can also just give a simple number like 5. You can give a number which is less than 255, it will get stored if it's an unsigned character. So no need to only put it in single quotes. You can, that also C allows, because characters are also treated like a small integer. So if I want to store a small number and operate on numbers, I can just store char C1 equal to 5. That also would work. Nothing wrong about it. But in general, we use it to store characters and so on. And to store a character, this is a convention that you have to follow. Put it in single quotes. Any text character, ASCII value automatically gets stored. Okay. Then there are a few other types of constant values that we often use. One of them is by using a preprocessor directive called hash define. Okay. So this is actually not a variable. One thing you have to understand here is when I define something like this, hash define maxlen 101, maxlen is actually not called as a variable. This is called as a preprocessor defined, string or a name, right? So it defines what is called as a constant identifier maxlen, which has the value 101. And what happens is in the code, anywhere if you have the string maxlen, the preprocessor will replace that maxlen with 101. So preprocessor is the one which handles the header files also. Or anything with this hash, right? In general, remember in C is anything that starts with hash in the first column, first line. Those are all things that the preprocessor understands. Okay. So if I have, for example, to explain this a little better, suppose in my file I had something like this, right? I had put hash define. So I say maxlen 101. Okay. So these also will typically come outside the function, just below the header file. Or sometimes these are all part of an header file. This hash defines you'll often find inside the header file also, but they'll all come into the program anyway. So after the preprocessor runs, maxlen has got this. I mean, maxlen is this is understood by the preprocessor. When the preprocessor runs, suppose you have your main function. Okay, here I have some variable called x. Somewhere here in the code, I have written x equal to maxlen. I have a statement like this in the C program, right? What happens is when the preprocessor runs, it would have first seen this maxlen. So preprocessor knows this programmer has defined a constant identifier called maxlen. It'll keep going through the file. So when it comes to this line, when it sees this maxlen, it knows I've already seen maxlen before, and it means 101. So it will just replace the file. This line will actually become x equal to 101. That's all. Before it goes to the subsequent compilation stage itself, the file actually gets modified. So this is a preprocessor defined constant. So when the preprocessor runs, this change happens. So preprocessor mostly does this text. This is called a textual substitution. Basically, instead of this symbol, this 101 will come in that place. Okay. So when the compiler runs, compiler is just going to see x equal to 101. It knows 101 is an integer constant and it will work as expected. Is that clear? So preprocessor essentially will substitute that string. So basically the modified C file is what the actual compiler runs. So preprocessor runs before the proper compiler runs. So before the compiler runs, this maxlen string is now replaced with 101. So when the compiler actually runs, it's going to see like a regular, integer assignment statement. Is that clear? How the preprocessor runs? Similarly, there are something called macros, which is also handled by the preprocessor. We will see that when we subsequently. Macros are again something similar. It's a textual substitution. I can do some operation. I can define something. Maybe just to give an example, probably. So I could have defined something like this. Okay. Something like this. So this is called as a macro definition. I'm defining a macro called add, which takes two parameters. And I'm just saying it is nothing but x plus y. So later in the code, somewhere if I had defined something like y is equal to say add 1, 3, right? The preprocessor when it runs, preprocessor will first see this definition. Okay. When it comes to this line will be replaced by this bracket will come as it is. Instead of x, 1, instead of y, it will be 3. So this line actually will get modified to y equal to 1 plus 3. And this is what will go to the compiler. Is that clear? So these are called macro definitions. Again, it's just a simple textual substitution. So all you have to understand is macros are nothing but simple. You can actually write some simple, something. It's like a function, but it's not, it doesn't actually make call and come back. It's like an inline change. So basically the same line, the code will come. Even if I add some 2-3 lines here, the code will just come there. Okay. So this is called as a macro definition. All these are part of, what we call as a preprocessor defined things actually. Okay. Then you have something called as a string constant. Okay. So we'll talk about strings later, but for now understand if I define something like this within double quotes, I put some text here. So this is called as a string constant. We'll see subsequently how a string is stored and all that, but this is a way to define a string constant. Generally this is stored in a area of memory. String constants cannot be modified. Generally it's a constant. So you store it and you can just use it actually. Okay. And in general, the convention for constant identifiers which are handled by the preprocessors, it's a convention. It's not like hard and fast rule, but almost all C programmers follow this. It will always be in capital, all capital. Generally, variable names, we will never use all capitals. Very, very rarely you use all capitals for a variable name. It may start with the capital letters depending on the coding guidelines that you have. You may use underscores and all that, but it will not be generally all capital. Generally, the moment you see in any C program something which is all capitals, you can be 99 or 100% sure that it's something which is defined in a header file. Okay. Typically, all these constants are defined in some header file. Sometimes it may be in the same file that you're reading, or it is in some header file. If you don't find it in the same file, then you have to go. Suppose you're reading a C program, right? And you're seeing something like maxlen. Then you go to the start of the program and see whether maxlen is defined there. If it is not defined there, you may see some header files defined there. Then you have to go to those header files and see where maxlen, one of them will have that definition. Okay. So that's how you understand where things are defined. So that's a convention which is good to follow because almost everybody uses that convention, like it's always in capital letters. Then there's something called const keyword, which is good to understand here. So this keyword, if you attach it before any variable definition, the language tells that this becomes a constant, which means this variable pi cannot be modified anywhere else. Okay, which means pi is a constant. Nobody should modify it anywhere later. What I mean is, suppose let's say we have defined something like this here. In my program, I had defined const float. It could be any type. I'm just taking as an example. Pi 3.14f. Okay. We know pi is a constant, right? Nobody should be trying to change that. Pi is a global constant. But later somewhere you made a mistake in your code. You are doing something like pi is equal to pi plus 1. Okay. What this means is I'm trying to add value of 1 to the current value of pi and store it back into pi. If pi comes on the left hand side of an assignment statement, which means it's a destination, which means somebody is trying to write to it, right? But the moment you have defined it as a constant, this is illegal. So if you write code like this, the compiler will automatically tell you there's an error in this line saying, attempt to write to a constant value. So it is a good programming practice for variables that are very critical. You are developing an embedded system. There are some important parameters which should not get changed by any occasion, right? It's a good programming practice to declare them as constant, so that as a programmer, if you made a mistake somewhere accidentally, you forgot, and you're trying to modify it, the compiler will catch that error for you. So it's a good programming practice to use the compiler to make sure that this variable doesn't get modified by some code in the whole file or in other files accidentally. Is that clear? So that's called as a const keyword, which is good. Similarly, you can put it for this also. Const char message, you say this, it indicates that that the elements of this array cannot also be altered. It's like a constant actually. Then we look at basic simple how to print messages and to read some messages. So the standards, this is part of what is called as the standards C library. So we use a function called printf. Printf is what we call it, and it's a function always takes some parameter. Function is something nothing but you can imagine the C function is nothing but a piece of code which does it implements some functionality. Printf is a function we call to print something on the screen. Okay? Now the first parameter to that is called as format string. Okay, we'll look at what it means. Then you give multiple arguments to it. Okay, to print something. The arguments are what you want to print, and how to print it is being told by this format string. This is called as the format specifier. We'll talk about it. And this format actually points to a string. It's a set of characters which will be null terminated. And in the format string, there are two types actually. One is normal characters which will just get copied to the output as it is. And there are something called conversion specifiers which are used to tell the printer how to deal with the arguments that we are giving subsequently. Okay. So don't worry if you don't understand. No, when I take an example, it will be more clearer. So there are two types. One is normal characters which will get printed as it is. Then conversion specifiers which apply to the arguments. And the conversion specifiers apply in sequence. The first conversion specifier is to first argument. Second conversion specifier is second argument and all that. And conversion specifiers will start with the special character %. Okay. So let's take an example and to understand. So important thing to understand, printer, the first parameter of the printer function is called as the format, which is always a string which will be in double quotes. Then you'll have a series of arguments which are the values that you want to print. How to print them is controlled by this conversion specifiers. Other than the conversion specifiers, if you have any other text within the double quote, they will get printed as it is. Okay. Now let's take some examples to understand how this really works. Okay. Let's take an simplest example, which all of us start with this simple program, right? We say printf hello world. This is the classic first program in C. Okay. Now, how many parameters does this have? It actually has only one parameter. This entire thing within double quotes, right? It is called a string, and this entire thing is just one single parameter. Okay, it's important to understand this. The first parameter is always enclosed in double quotes, and in this usage of printf, where we have called here, we have exactly one parameter, which is this format string that we have. And now let's look at it. Is there any percentage symbol in the string? Nothing is there. So now what does the rule for printf says? If there's any other character, it will just get printed as it is on the screen. That is how the printf specification says. So what is now going to get printed on the screen? It's just going to print hello world, and \n means it's a new line character. So after printing this, the next prompt, if you have C:, it will come in the next line. Is that clear? So this is how printf works. Now let's take another example. Let's say num equal to %d \n, a comma, then I'm saying value, some variable name. And before this, let's assume we have defined int value is equal to 11, something like this. Okay. Now, how many parameters are there in this call? This is the first parameter, which is the format string. And arguments are separated by comma. There's a comma here. Then you have this parameter, which is a variable name val. Okay. Now, what happens is printf will actually go through the format string. That's how printf works. As long as it keeps seeing the normal characters, it will keep sending it to the output. So as long till num0, it would have sent out these things to the output. So it will keep coming on the screen, assume. Okay. Then it sees a special character called percentage. Then it knows this is a conversion specifier. So the next character becomes important. Next character is a special character. So when it says D, it knows the user is asking me to print a decimal integer. Okay. So it knows this is what the user is interested. It knows the first argument has to be treated as a decimal integer and I have to print it in the decimal format on the screen. Okay. So val, once it knows this, it will go and read the second argument. Second argument, we are given the value 11. Or you have to keep imagining, as embedded programmers, you have to imagine 11 is nothing but a binary value which is stored in some memory location, right? So val is nothing but any variable will get some space in memory. Somewhere 11 is stored. How is 11 stored? In binary, which is we have seen yesterday some example 1011. So if it is a single byte, 1011, but we are declared as int, so all the upper bytes will all be 0. 4 bytes may be there, but upper bytes are all 0 because it's a very small number, only 1 byte is enough to store. So this is a bit pattern which is stored there. Okay. So val, it knows it is a value. In fact, in C, one more thing to remember is when you make a function call, the value is what is passed. So what the compiler would have done when it generates the code, right? It knows val is a variable. It would have generated code to take this value which is there in this location called val, and it will probably push it on the stack or something. Stack is a mechanism by which parameters are passed. We'll see that a little more later. But that value will go to the function printf. And printf knows where to get that value. Where it's set off in a stack, you can have multiple variables in the stack. So printf knows the first argument is going to be these 4 bytes. It will go read that. And then it will generate. Now it has to, what should it generate? To print something on the screen, you are again generate the ASCII values to be printed on the screen, right? So it knows the quantity is 11. So there is a part of the code of printf. It will generate those ASCII characters 1 and 1 so that finally on the screen you will see num equal to 11 getting printed. So this for you to understand. If it's confusing, don't worry about it at this stage. All you remember is whatever value, if you give percentage %d, printf will do whatever is required to print it as 1 and a 1. Okay. The same example, instead of saying percentage %d, if I had told percentage %x, okay, if I had told it as percentage %x, it means we are telling printf treat the first argument because this is the first conversion specifier. When I say percentage %x, it means printf has to treat the first, it has to print the first argument as it is an integer value, but print it in an hexadecimal notation. Okay. Again, what is stored in memory, you can see this binary bit pattern is stored. That is what is being sent to the printf function also. But now printf will have logic. What should it print? What is the hexadecimal character for 11? Hexadecimal character for 11 is B, right? 0 to 9 you have, then you have A and B. A is 10, B is 11. So for the value 11, decimal 11, now what will get printed on the screen? It will just say NUM equal to small b. If you view small x, it will print small b. If you view percentage capital X, it will print capital B. That's the convention. Okay. And in general, programmers, for us to make sure that we remember what we printed, right? We always generally printf, we will say 0x percentage x. Okay. So this 0x is just not a special character. So printf will just print NUM equal to 0x. Then it will see percentage, oh, percentage has come. It's a conversion specifier. Then it sees x. Then it knows I have to treat that argument as an integer, but I have to print it in hexadecimal notation. So it does all the logic required to generate the ASCII value of B, and that is what will be sent to the display system. The display system shows B for you. Is that clear? How printf works really? Suppose I have multiple parameters. Let's say I have 2 parameters. Or I can even print it directly. I don't need to even declare a variable. I can just say printf num1 equal to say percentage d, then comma I say num2 is equal to percentage d \n if required. Then I can just even give the numbers here. I can give 8, 23 like this. Okay. So what will happen? Num1 equal to will get printed. Printf sees this percentage and it sees a d, and it knows the first parameter should be printed as a decimal integer. It goes checks the value 8, so it will generate whatever is needed to print 8 on the screen. Comma it sees, comma will get printed as it is. It's not a special character. Then NUM2 will get printed as it is. Equal to will get printed as it is. Then it sees another percentage. Then it knows, okay, one more conversion specifier. And this applies to the second argument. First argument is already done, so it's a second argument. So it will go and sees what is the specifier? D, which means again decimal value. Then it goes, gets the second argument, which is 23. So it will just print 23 in decimal, then \n, so a new line character will get printed. Is that clear how printf works? So you can have any number of arguments like this. So only thing to remember, the common mistakes people make is for every format specifier, there should be an argument. It's a mistake if you have a format specifier and not have an argument, or vice versa. If you have no format specifiers but you are giving arguments, in that case, okay, nothing will get printed, it will get ignored. But if you give percentage D and don't give arguments, right? Normally the good compiler will give you a warning or an error saying that, there is a mismatch. But some compilers may not give you a warning or an error, depends on the compiler. Then what will happen? Some junk will get printed. So if you give some format specifiers but you are not really parsed, right? Some garbage can get printed. But modern compilers, many of them do give you a warning because they understand printf. They parse the thing properly. Some modern compilers try to help you a little bit more. But 20 years back, compilers will not do all that. If you had given a percentage D, not forgotten to give this, right? Some garbage will get printed because it would access some memory location, whatever was there, it will get printed. Okay. So important things to remember. In printf, anything other than percentage followed by thing, it will get printed as it is on the screen. Moment printf sees a percentage, it will check the next character. The next character determines how the corresponding argument has to be treated. And there's a one-to-one mapping. First conversion specifier for the first argument, second for the second conversion specifier for the second argument, and so on. Is this clear how printf works? And as a programmer, we have to always make sure the number of format specifiers matches with the number of arguments that we are giving. Clear? Okay. So what are all the format specifiers quickly? So this is something called D. I also can be used. Then O is for octal. X we saw is for hexadecimal. U to treat the number as an unsigned decimal, you can give U. Like when you have unsigned quantity, if you give D, it is treated as a signed quantity. The same location, if you want to treat it and print it as a unsigned, you have to give U. For an example, right? Assume, let's say in one memory location, right? We had the value say 255. Okay, one character, I have defined it unsigned, I have stored 255. So if I try to print that location using percentage D, it will actually get printed as -1. Because if you treat it as a single character, and it will get printed as -1. If you give percentage U, it will get printed properly. So you have to be clear about how you want to store it and print it. This is especially important when you are extracting some piece of things from an integer and how you print it. So you have to be clear. In embedded, many times when you want to look at bit patterns and all that, we use hexadecimal. So it doesn't matter because it just comes as an hexadecimal notation. But sometimes you have to be aware of, why suddenly you see a negative number. You should understand maybe because a sign bit and you're printing using percentage D, you can look at it. So if you want to print a single character, suppose I have stored an ASCII value, right? So we saw an example here. Suppose I have a simple code here. I have declared a variable char C, or let's say C1, and I'm saying C1 is equal to H. Okay, and I want to print this, and I want to see H on the screen. Right? How do I do? I can just say printf. I have to say percentage C, and the variable name is C1. So then, when this program runs, you will see H printed on the screen. So percentage C tells the parameter that is being passed. This is where you have to understand what it really tells printf is the parameter which is passed. Again, some binary pattern, right? It tells printf treat it as an ASCII value and generate the appropriate things to print that on the screen. Okay. So in fact, I had written like this. Suppose into percentage C, if I had done something like say printf percentage D C1, what do you think will get printed? I had written a code like this, C1 equal to H, but I want to print, but I don't use a C specifier. If you use D, what will happen is, because printf doesn't know, all it is going to get is it's going to get one bit pattern passed on the stack or somewhere. Now it will think, yeah, somebody has given me an integer. It will try to treat those bits as an integer, decimal integer, and print. In this case, yeah, H probably has, I don't remember, it's like it starts from 65, 66, 67, something like, okay, Hij, maybe 72 or 73. You will actually see 72 or 73 getting printed on the screen. Is that clear? So this is how, that's why I said printf, it gets a bit pattern. How to print it is the format specifier's job, because all it gets is a binary pattern. This is where understanding always that, everything is stored in binary is important. ASCII is also binary bit pattern only. So you tell printf that is ASCII value, it knows how to handle ASCII value. It will generate the font for H or whatever and print it. Or if I tell it percentage D, yeah, it will treat it as a number and print it as a number. And you can tell printf to print it in decimal format, hexadecimal format, whatever. But finally everything is, what is stored is one bit pattern. Okay, is that clear? So, and similarly, if I want to print an entire string, right? Okay, we saw how a string is nothing but a set of characters. We use something called percentage S. And if to print floating point numbers, we use percentage F for percentage D. Okay, and with this exponent notation. If you want to print with this exponent notation, it is this. And if you want to print the character percentage itself, right? Suppose I want to show print a message saying the percentage of interest or something. I want that symbol percentage itself. Then you put percentage. So you two percentages. It knows I had to just print a percentage. Is that clear? So printf, important thing to understand. The first parameter is a format specifier. Then you have a series of arguments. Then you print that actually. So we have examples we have already seen. We'll, for example, you can see here int x equal to 31, and you can just print percentage d. It will print 31. 31 will come on the screen. The same x, if I do percentage x, what will get printed? It will print 15, because 15 is nothing but the hexadecimal notation 31. Because 1 means first position 16 plus 5. Actually 31. I think it's wrong. It's not. Is it 16? Maybe I made a mistake. It's not 15 is not 31. It's 21. So it will print something else. I had to correct it. Okay. What should it print? Can somebody convert 31 in hexadecimal? It will be 1f. 1f is 31. It will not be 115. It will be 1. So 16 plus 15 is 31, right? So it will print 1f on the screen. Okay. C1 equal to m. I am declared it as a character constant. This is called a character constant. If I use percentage C, character m will get printed on the screen. Okay. So this is like an example of a string constant. If I put percentages my MSG, you will see the string hello students getting printed. Is that clear? So how the different format specifiers work. Okay. Similarly, if I want to read something, right? Printf is for printing. So read is to read something from the keyboard, right? Somebody user is typing something. They want to read something, which is an equivalent function is called scanf. Okay. Syntax is quite similar. Scanf, you will again have a format specifier which tells what type of arguments I'm going to be inputting. Okay. And important thing to remember is in scanf, the variable names will be specified with an ampersand. We'll talk about it when we go to pointers. For now, understand, because scanf is reading something and it has to store that value in a particular variable name. Because C uses what is called call by value. If I just say x, only the value of x will go to the function scanf. It doesn't know where to store it. So I'll have to send the location where that variable has to be, whatever somebody is typing has to be stored. So I'll have to send to scanf an address where I have to store that location. I want to store it in the location in a variable called x. So then I have to send the address of x. So the symbol ampersand means address of, and that is what is going to be stored here. So I'll probably just quickly run through, just show you a couple of examples in this online compiler and then break right now. So let's see, this is an online compiler. Okay. So let's do some simple variable declarations and printf statements here. Let's declare say int x equal to 2, y equal to say 31. Okay. And let's see how it behaves. Let's say I am printing x normally. I'll say x, I can just say x equal to percentage d and say y is equal to, I want to print it as an hexadecimal number. Okay. I'm just saying y equal to percentage x and I'm just trying to run this program. Okay. So what is the mistake here? Why is it not printing properly? Can somebody tell me what is going on here? What is missing? What is missing? The arguments are missing, right? I didn't give the arguments. So you can see some garbage is getting printed because the printf sees this and it thinks there is something on the stack. If some modern compilers give you an error, so I should give x comma y here. So if I give x comma y, then I run it. Can you see 2 is getting printed as it is in decimal format? 31 is getting printed in hexadecimal format. Is that clear? If I add a character constant, if I say char c1 equal to say hg or something like that, right? How do I print it? I can just use printf c1 equal to, the c1 equal to is not mandatory. I could have just printed as it is, but just for us to understand what is getting printed, right? So it is just for us to understand. Okay. Can you see? It is printing G properly. Okay. Instead of percentage C, if I had say, for example, given percentage D, let's see what will get printed. It won't print G, it will print something else. So it's printing 71, which is nothing but the actually ASCII code value. This 71 is ASCII code for C1. Is that clear? So how printf can be used? Similarly, scanf. I can just quickly show something with scanf and stop there. This online compiler works fine for that. I want to read a decimal number, okay, and I want to store it in y. So I give address of y, and let's print and see whether the value has got stored properly or not. So I put a semicolon everywhere. So okay, now the program is waiting because that scanf is there. So let me type 123 and then press return. You can see y is equal to 123. Is that clear? So that's how we can write printf and scanf. And so we'll kind of stop here. We have seen basics of C structure. What is a typical C structure of a C program? We saw what are data types. We saw what are variables, and then we saw how to do some basic printing of some messages on the screen, format specifiers for that, and how to read something.